10.5. The capacity, oh, wrong class again, 6.5. All right, I'll get this under control soon. All right, so this is section 6.5. I should write this down somewhere so I remember. 6.5, this is number 5 from the online homework. And in Math 243, and just in case you've never noticed this, see these little numbers in the upper right corner there? That the 6.5.11 means chapter 6, section 5, problem number 11 in the book is almost the same as this one. So if you ever want a book problem to test, like if you're having trouble with something and you had to use Help Me Solve It a lot, or view an example, you might check out the book version. Okay, so the capacity of an elevator is 8 people, or 1,344 pounds. Okay, so capacity. This is number 5. Capacity is 8. That implies a total weight of 1,344 pounds. What the hell is the abbreviation for pounds? LB. Where the hell does that come from? I can't remember. I used to know, but I don't know. Okay, anyway. The capacity will be exceeded if 8 people have weights with a mean greater than that mean. So let's just check. What is 1,344 divided by 8? That would be the average weight out of 8 people. 168, okay. So the capacity will be exceeded if 8 people have weights with a mean that's greater than that, okay. So let's say W with a bar over it is mean weight. Oops. Mean weight. So if N is equal to 8, then we don't want W bar to be greater than 168. So we could have people less than that, people more than that, but if the average of all 8 people is greater than that, then we've exceeded the capacity of the elevator. Does that make sense? Okay. All right. Suppose the people have weights that are normally distributed. Okay. So just on the test, you'll use the normal distribution if it says things are normally distributed. So the problems that are normal are pretty darn obvious because they say assume normal distribution, blah, blah, blah. Binomial problems will not say normal distribution, and they'll generally give you a percentage of something to start with, right? So in my other class, they were asking, how do I know the difference between normal problems and binomial problems? Binomial problems start with a percentage of some kind. Normal problems say in them somewhere, assuming a normal distribution. Okay? If we assume a normal distribution, we also need to know what is the mean. So here, the normal mean is 173. Okay? And normal standard deviation is assumed to be 31. Okay, so that's all the information we need to start answering some questions. So let's see what questions they have for us. So back to the homework. Find the probability that if a person is randomly selected, his weight will be greater than 168 pounds. So we're looking at a single individual. So regular binomial probabilities are about a randomly selected individual. Okay, so this is about this is a regular normal calculation. So I need to draw a picture of this. So I want to know what is the probability that a randomly selected individual male will have a weight greater than 168 pounds. So new page. Probability that a weight W is greater than 168. And again, the key here is we have a randomly selected individual. Picture to go with that. Let's draw that up here. Draw your best normal curve. Mean 173. So is 168 bigger than or smaller than the mean? It's smaller. So one standard deviation below the mean would be 173 minus 31. which is what, 142? Is that right? That's one standard deviation to the left. Now the reason I'm doing that is I just want to know about where 161 sits in the scheme of numbers on this axis. So 161 is going to be kind of in the middle, isn't it? A little higher than the middle maybe? Like let's say right there. That's probably 161. Or 168, sorry, I don't know where I got 168. 160. Okay, no. Why screw this, right? Okay, 168, sorry. 168 to the best of my estimation is about there, if that's 142 and that's 173. And I want to know when weights are greater than that. So that means I want to calculate the right tail here. I need to find this area. Remember, on a normal distribution, they go to the right forever and the left forever. So the calculator's version of going to the right forever is 1 times 10 to the 99th. That's what that means. And the calculator's version to the left forever, anybody remember that one? Yeah, negative 1e 99, which is 1 times 10 to the negative 199 power. So what formula do I want to use here? Normal CDF. Will we ever use the PDF? Never. Unless on Excel it would be norm.dist, correct. Hey, we've missed you. It's been a while. Your hair looks longer. All right, so the calculator wants to know what is the left-hand bound, what is the right-hand boundary, what is the mean, and what is the standard deviation. If you're on Excel, it uses norm or OpenOffice, or most of them, norm.dist or just norm.dist. It's norm.dist with Excel. And it wants X first, and then it wants mean, standard deviation, and then cumulative or not. And we're always going to do cumulative, so we're always going to put true there. Now the catch on Excel is Excel only gives left tails. So if this is my X here, Excel is going to calculate that side there. So to get the right answer for Excel, I would want to do, for a right tail, 1 minus the norm dist on Excel. You type equals 1 minus norm dist and then throw in the numbers. All right, so I'm going to do that on my TI, and I'm going to do it on X would be the 168, correct. So second quit or clear. Let's see, I want distributions, normal CDF, lower bound is, so the lower bound is on the left, that's the 168, right? The upper bound is on the right, that's forever, which is 1 second comma for the E, 99. My mean is 173, and standard deviation is 31. Does that sound right? Let's go back and look just to make sure. Yep, 31. Calculator, and I think those are all the relevant numbers. Paste and enter. Calculator says there's about a 56.4% chance that the weight of a randomly selected individual will be greater than 168. That's what that means. So again, I entered here norm all CDF. I think I need to switch to the up pen on the board. 168, 1, come on, E, 99, 173. So on the test, you have to write down what you typed into the calculator or what you wrote on Excel if you're going to use Excel on the test. 31. I want to know exactly what you typed, make sure we get them in the right order, and we calculated this is about, was it 53.4? 56.4, thank you. 56.4. I want to, yeah, anytime it's normal, I want both the picture and I want the formula that you used, whether it's this one or this one. Yeah, so down here, I would have typed 168, comma. I don't necessarily need every keystroke when you're doing some kind of arithmetic, but if you use a formula, I need to know what formula you used and what numbers you entered in what order. If you have a drawing, I would like some numbers on the drawing. Yeah. So just doing this and this and that would be like a pitiful drawing. I would like at least a couple numbers on there. At the very least, I need the 168 on there in the mean, I would say. Okay. I do that. I like to either use z-scores or write down the standard deviation values so that I know where my number sits. Because one thing about that, since I know that this number is to the left of the mean, and the mean has 50% to the right and the left, I know my answer's got to be greater than 50%. So I can give it a ballpark just by looking at the picture. Does that make sense? So it's just a good guide to me to make sure I push the right buttons on the calculator. Because is it easy to screw up the buttons on the calculator? Hell yes, I do it every day. So we should, so the picture helps me keep myself in line. Yeah, so I don't, yeah, so if you just rounded to the nearest percent, sometimes that's okay, sometimes it's not. Usually I go to 1 decimal place as a percent unless I have a good reason to go more. The homework does 0.2% or 4 decimal places of a regular number. Yeah. That's fine too. I get used to doing it one way. Yeah. Yeah. So if you were doing it the homework way, they would have included 1 more decimal place, and they usually don't write it as a percent. They give it as a decimal. So what would be the next place here? 1. And on the homework, they would say write it as 0.5641. But usually I'm thinking about I'm going to tell my mother about this, and so I write it as a percentage to 1 decimal place because she gets fussy if I give her more than that. How will we know that you want a percentage? If I want something other, I'll tell you. But in general, all the questions, I'm going to want you to write a sentence that my mother would like. So I'm going to want a percentage in most cases. Yeah, not the decimal version. Can I understand the decimal version? Sure, I can understand that totally fine. But I want my mother to be able to, sit down with me and a beer and read these tests and say, oh, this is interesting. Okay. No, she doesn't drink beer and she would not want to go over these tests. Remember, my mother is a numerologist and energy healer, not a statistics teacher. So that won't happen. But we do talk about math all the time. One can only hope someday. Okay, let's get to the next question. I am, yeah, if I can find it here somewhere. There it is. Okay, so they want 4 decimal places, so 0.5641. Good job. Excellent. Okay, find the probability that 8 randomly selected people will have a mean that is greater. Okay, as soon as we start taking groups of people and we compress their data to a mean, that's what the central limit theorem talks about. So let me just remind you about the central limit theorem, and then we'll do that. So we have 8 people, and we're looking at the mean. So I'm going to write on the board, central limit theorem. It says a lot of things. I'm just going to give you the part that's relevant to this problem. Central limit theorem says that if you have a bunch of small samples, then the mean of the means of those samples will be approximately equal to the mean of the population. It also says that the standard deviation of the means is going to be approximately the standard deviation of the population over the square root of your sample size. Other thing it says is that n should be greater than 30, but oops, I missed a number. There we go. Should be greater than 30, and we can cheat that. The book gives one major reason we can skip that constraint. The standard deviation of the means of the samples is approximately equal to the standard deviation of the population divided by the square root of the sample size. That's what the central limit theorem says. And it also says that your sample size should be greater than 30 for this to be valid, except under what condition? Yeah, if it's the book says normal, I claim uniform is also you can get away with it too. But the book says normal. So you can cheat this if your population is already normal. You can cheat with n less than 30 if the population is normally distributed. Now this isn't in the book, but Gary claims, I claim, that you can also get away with this with a uniform distribution. I did that before. I was hoping I didn't as I pushed that. Gary claims uniform is okay too. Okay. So in the example in class the other day, I was playing around with sample size 5, and it came out not bad. 5 is a far cry from 30. But if it's normal, you can definitely get away with less than 30. Less than 5, that's pushing it. I wouldn't do that. But here we have a sample size of 8. So here we have n equals 8, and we have the mean of 8 weights is 168. And so we want to know what is the probability that the mean of the weights is greater than 168. Now, I just need to describe what the central limit theorem means to me. When I look at the mean of a group of data, I've gotten rid of a ton of information. I just threw it out, right? There were originally 8 people, and they each had diverse weights. Now I'm just saying, on average, you guys are 168. So I compress the data to a single point. When you compress data, you're compressing the distribution, and that's why we have to divide the standard deviation by the square root of n. We have to compress, because that's what we did to the data. So the distribution gets compressed too. And the square root of n turns out to be the ideal compression factor. Okay.
Wait, so, and then how do you know if it's normally distributed?
It's claimed.
They claim it.
Yeah, we claim it up front. Yeah, we have to make an assumption about that. Okay, so all the problems that involve normal distributions or uniform distributions, there will be a claim. It's assumed that weights of people are normally distributed, or it's assumed that the month somebody is born in is a uniform distribution throughout the year. If we don't have that assumption, then n has to be greater than 30. Then we can use the theorem. So it turns out if n is greater than 30, this applies to any distribution, no matter how weird.
But if it's not, let's just say it's 10, but it's not.
If we only had a sample size of 10 and it's not uniform and it's not normal, then the results I get from this may be just bullshit. Central limit theorem doesn't really apply. I could try to apply it. I might get lucky, but there's no guarantee. Yes, there are other methods you can use for problems like that. Yeah. And that's an area called non-parametric statistics, which is cool stuff, but we're not going there. Okay, so I'm going to redraw my distribution. Mean of my distribution, according to the central limit theorem, stays the same. That's still 173. The standard deviation has now shifted. So because of that, n equals 8, my standard deviation is now 31 divided by the square root of 8. Now, so far we've been calculating weights to the nearest whole number. So you can give me that to the nearest 1/10 of a percent for now? Oh, sorry, 1/10? What's that? It was given in the original problem. What's that? No, the mean was given to be 173. Yeah, and we're asked what's the chance that the mean weight of 8 people is greater than 168? That's what this says right here. So what is approximately to 1 decimal place 31 divided by the square root of 8? 10.96. Okay, so we'll call it 11.1. 11.0. Sorry, I don't know where I got that from. Okay, so we're just going to call it 11. That's kind of nice because now I can go standard deviations on each side. So one standard deviation to the left will be what? 162? And my now usually I do multiple ones, but I really don't need to because I just need to know where does my number sit. So my number sits pretty darn close to the middle of that interval, huh? So that right there is my 168. So in this case, relative to the standard deviation, 168 is not as close to the mean. Yes, no, maybe? In this case, since my standard deviation shrunk, 168 is not as close to the mean as it was in the other distribution. To justify that, I could find the z-score in this case. So the z, no, I'm just messing around. Yeah, so I'm just, do you guys remember what a z-score is? How far is it from the mean, right, in terms of standard deviations? So that means we take the number we're questioning, 168, we subtract the mean, 173, and we divide by the standard deviation, in this case is 11. So what is 168 minus 73, right? That's going to be what, 5? 5 over 11 is going to be 0.4-ish, 0.5-ish, somewhere in there. Negative 0.45 repeating. Okay, that's the z-score of the mean weight of 8 people being 168. Let's go back on the other problem for a minute. What's the z-score for an individual that weighs 168? So I'm going to squeeze it right here. Here it would be 168 minus 173 over 31, which is still 5 in the top, but this time we're dividing by 31. Oh, negative 5, thank you. And that's going to be about what? Negative 0.2 decimal places? Okay. 1/6, yeah. Yeah, it's about 1/6. Negative 0.16. So since the standard deviation is wider here, 5 is closer z-score wise to the mean than in this narrower distribution here. Probabilities will change, right? So now we calculate this probability either on Excel or on the TI. Did anyone get that probability? To 4 decimal places. 1 minus the norm dist, because we're switching the tail side. 1 minus to switch a tail. All right, so I'm going to try it on Google Drive just to be different. Standard deviation is about 11 here, or you could call it 31 over the square root of 8, which is what I'm going to call it. Let's make sure we're all getting the same number. We draw our picture. So equals 1 minus norm dist. So on Google Drive, it does not have a dot in it. And x is 168. The mean is 173. Standard deviation is 31 divided by the square root of 8.
So your standard deviation is 31 divided by
Square root of 8. Yeah, so I just actually, in the place in Excel, it asked for the standard deviation. I just typed SQRT of 8 under 31. I'll write it out, what I typed in just a sec. And then this is cumulative. That is true. Close parentheses, hit enter. And if I got lucky, I get about 67.59%. Anyone else get that? Yeah. So I'll write both versions of the formula up here. So on Excel, I had 1 minus, or on Google Drive, norm dist there's a dot in the middle with Excel. There isn't in Google Spreadsheets. And I typed in, what do they do? 168, 173, comma, then underneath, then next I did 31 divided by, oops, that's not a 1. (31 divided by SQRT is square root there, and then I did comma true. On the TI, I would type normal CDF, left-hand number is 168, right-hand number is infinity, mean is 173, standard deviation is 31, and there I could actually use the square root symbol. Now, if you use 11 instead of that, you'll get a slightly different answer because that's rounding. So I'm approximating twice in a row. So let me type that here. So all I'm going to do is tweak my formula here by dividing by the square root of 8. And I should get 67.59. If I use 11, which is the approximate version of the standard deviation, it'll be a slightly different answer, which is fine. I get 67.53%. Okay, so the first 3 decimal places are great. My mom would be happy with that. Yeah, that throws it off, right? So here's the big thing. So when do you use the central limit theorem? And what the central limit theorem is all about means. So anytime you're asking a question about the mean of a sample, that's the central limit theorem. And that's when you have to adjust your standard deviation to compensate for compressing the data. Really?
So annoying.
Oh, it doesn't load right. Look at that.
Well, I had it.
Is it the wireless issue or what?
Like this.
Okay. You think that might have something to do with it?
Well, that's why I had that.
Huh.
Yeah, it always.
That's weird. You have the same problem? And when you resize the screen, is it? Or just the homework just doesn't load properly? And it just dies on you?
And like last chapter,
Huh.
anytime I get one wrong, I'd have to time back in. So it was like a definite. Like, I don't want to get anything wrong. I'll just time back in.
What browsers are they using?
You got it wrong.
I don't know. What browser are you using?
I've had problems in Chrome and in Internet.
Oh, okay.
Firefox is the same.
I tend to use Firefox for the online homework. I find it works the best. Chrome works okay. I just avoid Internet Explorer anyway. That sucks. So if you're ever so frustrated with the online homework you can't stand it, I will be glad to trade online homework with book homework for you. So just let me know. I can give you a list of equivalent book problems. Well, you can because there's half the answers are in the back of the book and I have an answer key over here in my office. So you can feel free to use that anytime you want. All right. What's that?
I only have the online book.
So?
So what page would it be?
Well, you just look at the homework in that section. You can do
But
that.
I checked my
Because the answers are in the back online, too. Well, okay, hang on. Everyone take a deep breath. We're going to do a problem in the book once I type this in. So what do I think the answer is? 0.56. Oh, help me out here. 8.3 if I use the 11. Let's see if it takes that. No? Oh, 7. Oh, shit. I'm way off. Okay, this class is degenerating. Oh, 6. I'm going to use the 11. I want to see if it takes it. 7.53. Ah, it's not correct. It doesn't like that I rounded. So it doesn't like that I rounded. I know. But will it take an 8?
Oh, yeah, it's right, 9 'cause it's
Ah, it takes an 8. So usually, yeah, usually what they do is for these problems, they have a number in the middle, plus or minus like 0.001, or in this case, 0.001.
But what about on the test if we put 0.675?
I will be fine with either of these answers on my calculator. So points, as long as you tell me what you did, and the answer's in the ballpark, and you know what it means. What does this answer mean? Let's do that, and then we'll do a regular book problem. Oh, there's more. Oh, this is going to help me figure out what it means. Maybe before we do that, let's write our own sentence as to what it means, because on the test you're not going to have multiple choice questions to choose from. So this is about 50, what is it? 56. Thank you. 67.5ish, right? Okay. What does this number mean? We calculated it. That's fine. You're missing some relevant facts.
Can we read the question?
Yes. Question says, oops, wrong button. The question's, oh, come on. Find the probability that 8 randomly selected people will have a mean weight, a mean that is greater than 168 pounds.
So it's the probability of 8 random people being over the mean?
Yeah, just restate the question, right? Yeah, so it's the probability that 8 randomly selected people will have a mean weight that is greater than 168. Is that a problem for this elevator? Yeah, you're over capacity for the elevator. What's the probability we're going to be over capacity on the elevator for 8 people? 67% of the time we're over capacity. This is a problem, right? Yeah. So what this means is 67.5% of groups of 8 people will have a mean weight greater than 168. So yeah, we could also say that have a combined weight of greater than 1,344 pounds. Yeah, you could also state that. My mother would probably like that better. Or a combined. You didn't tell me about the 8 people combined. Oh, you did say full capacity. Okay. You're right. I'm wrong.
Yeah, but, some people's mothers like to be reminded.
Yeah.
You don't want them to like scroll up and like.
What was that of capacity again? Full? What's full again, Gary? I can't remember. Like alarms go off if the weight's exceeded? Yeah. Some do have that, yeah. Yes, Michael.
All right, so for the second
Yeah.
this is, I don't remember, for the second standard deviation, but the number divided by the square root, and what was the number you square root by?
The n, the total number of people involved. Yeah. Yeah, so you'd be divided by the square root of 15, right? Yeah, that's your sample size.
So is number 2 just like 5?
Oh, hang on, I'll look it up one sec. I just want to look at the online book just for fun.
Hey, good job.
All right, so. Okay, so let's see. I had one more part in my homework. Where the hell did my homework go? Oh, there it is. Does the elevator appear to have the correct weight limit? Why or why not? I would say no. There is a good chance that 8 randomly selected people will exceed the elevator capacity. Or no, 8 randomly selected people will never be under the weight limit. That's not true. Yeah, so it's a good chance. What's a good chance? 65-ish% or 67-ish or whatever we found. Yes, good job. Okay, so you had a question about number 2.
Yeah, is it like number 5?
Assume that this is number 5 in the book, by the way. So let's look in the book. Oops, wrong book. That's calculus. I could have sworn I brought up this book. Huh. Oh, that was the calculus book. Oops, let me switch. Sorry. Statistics, there we go. Number 5 in section 5. Oops, let's, this is counting down on me, postpone. Chapter 6, section 5. Come on, baby, you can do it. Multimedia textbook exercise sets, getting closer. Okay, so we want number 5, which apparently is on the next page. So answers, if you go to the table of contents and then you go to the appendix, answers to selected exercises, you can look up answers there. And they have answers to some of the problems, and then I have a complete solutions manual in my office that you're welcome to look at anytime. All right, so let's make that go away. So number 5 says, okay, using the central limit theorem, assume SAT scores are normally distributed with a mean of 1,518 and a standard deviation of 325. I am going to make that bigger, yeah. Yeah.
Using norm.dist, or why does it ask true or do you ever put false?
No, false would mean we're doing a PDF calculation with the normal, which is probabilistically useless. No, you're not going to use false, ever. Binomial when you use it, yes. That's for a single probability. For a single probability with normal, it's useless. It's only there for people that do calculus, I think. You can use it to make graphs of normal distributions, but not calculate probabilities. Okay, so let's see, what do we got here? Yeah, so this is pretty similar to the problem we just did. So we have a mean of 1,518. Let's switch colors. Standard deviation is 325. We want to know if one SAT score is randomly selected. So an individual, that's a regular normal calculation, find the probability that it is less than 1,500. So this one is actually not too bad. 1,518 is in the middle. 1,500 is smaller than that. One standard deviation below 1,518 is what? What's 1,518 minus 325? What is it? 1293. So 1,293 is one standard deviation below. So as far as z-scores go, this is a z-score of 0, this is a z-score of -1. 1193? Okay. Okay, 1193. So that's one standard deviation to the left. So the number I'm interested in is 1,500, which is pretty darn close to 1,518. It's right there on the edge of it. So that's my 1,500. So could you ballpark a guess at what is the probability that the SAT score, let's call that X, is less than 1,500? So what is this area right here approximately? Somebody give me a ballpark. What is it? 50%. It's going to be about 50%. Pretty darn close. Because 1,500 relative to the standard deviation is pretty close to 1,518. If I was using the TI, my calculation would look like this. Normal CDF. Left-hand boundary is what? Negative infinity. That's the left side. The right side is the 1,500. the mean is 1518, and the standard deviation is 325. And that should get us relatively close to 50%. 4 decimal places, what do we get? That's greater. Oh, did you do 1 minus? Oh, no, so there's not a 1 minus. Did you do 1 minus on this one? Okay, it shouldn't be a 1 minus. That 1 minus is a right tail.
So if I wanted to find the in between, would I do the left tail and the right tail on both sides and then take the middle string too?
I'll do one of those next.
Or do left tail and then greater
Left tail minus left tail. Big left tail minus little left tail. No, something's wrong with that. That looks more like it. 0.4779. Okay.
Those would be normal distributions, right?
Yeah. Yeah, I'll do one of those in just a minute. All right. So what does this mean? It means there's a 47.79% chance that an individual will have an a randomly selected individual will have an SAT score of less than 1500. That's what that means. Randomly selected individual. Okay, next question. What if 100 SAT stat scores are randomly selected? Find the probability that they have a mean of less than 1500. So now we're taking 100 people's scores and compressing them down to one score. How do I have to change what I'm doing to get that calculation? Central limit theorem, yeah. So I'm going to have to adjust the standard deviation by dividing by the square root of 100, which is 10. Dividing by 10 is easy. Yeah, so that just changes this a little bit. So for part B, the mean is going to stay the same. That's going to be 1518. But the standard deviation, because we're talking about the average SAT score of a bunch, is going to be 325 divided by the square root of 100, which is 32.5 exactly. And I want to know, what is the probability that the mean score of 100 people is less than 1500? So draw a picture of that. You owe somebody donuts? Cool. I heard the donut shop in town makes them late at night, and so I'd appreciate my donut warm, Daniel. All right. Yeah, me too. I haven't had lunch yet. Okay, so 1518 is still in the middle. What is one standard deviation to the left this time? 1518 divided by 32.5? I mean, sorry, minus 32.5? What are we at? One standard deviation to the left? 1485. 85? 0.5. Yeah. That, what was one standard deviation before was 1,100 and something, right? So this is a lot tighter. The 50. Oh, that's my favorite one. Fantastic. I like Fantastic because my favorite Doctor was the Ninth Doctor, and he used to like say Fantastic a lot. I don't know if you guys watch Doctor Who. Yeah. So this time 1500 is about here.
No, you're wrong. Stop trying.
So 1500 isn't right on the edge of the mean this time. It's kind of in the middle of one standard deviation to the left. And I want to know the probability that the SAT score is less than that. So if I were doing this on Excel, I could just type norm dist dot dist, and x is 1500. The mean is 1518. And the standard deviation is 32.5. And Michael, is this true or false
What?
for cumulative?
True.
It is true. Good job. All right, so I'm going to ask Google Drive about that. Maybe. Give me a minute. Where's my drive? Okay, let's.
It's stupid. On the part where you choose between all the words, it has the A, B, C, D. You choose. I'm pretty sure I know the right one.
Okay, equals norm. Oh, it froze up on you, so you lost it.
I get it wrong.
Norm dis, so 1500, 1518, 32.5. Uh-oh. So I get 28.98%, quite a bit lower than before. Right, so I'm gonna have, I love GeoGebra, I'm gonna have it draw it too, because it does such a sweet job. Mm-hmm. Yeah, I can show you both distributions here. Well, that's a good question. If we went one standard deviation to the left, so let me just do that calculation for comparison. So what if I just did norm dist, where I'm going to use z-scores. So let's say I use a z-score of -1, so go a whole standard deviation to the left, comma, the mean is 0, standard deviation's 1, and this is true. Yeah, because the way the curve slopes down. So the probability of being below 1 standard deviation from the mean is about 16%, right? And we're right in between halfway and 1 standard deviation to the left, so we ended up with like 30%, just the way it falls. It's just because of the shape of the normal curve. So I'm going to draw this normal curve just to show you. And that's one nice thing about GeoGebra. It draws these for us. Which one do I want? This one. Mean is, so for the new distribution, mean is 1518. Standard deviation is 32.5 and x. And so now I just need to go to the relevant part of the graph, which is way to the right. I know there's an easier way to do this, but I'm almost there. Okay, it's right in there. And if I bring my scale up, you'll see my normal curve start to bubble up here. No, isn't it cute? It's a cute little normal distribution. All right, so we'll stretch you out just a little more. Okay, so this is the normal distribution for groups of 100. So now I'm going to compare that to the normal distribution of an individual. Check it out. Look at the difference. The normal distribution for an individual is a lot lower and wider. Standard deviation is 325. Normal distribution for groups of 100, because we're averaging them all into a single number, is much narrower and pointier. And so the calculation we just did would be the following. And GeoGebra actually has a little infinity symbol, which is kind of cute. From negative infinity all the way over to, what is it, 1500? And it's thinking, there it is right there. And it says it's about 29%. Yeah. So when I'm writing tests, this is what I use to make graphics that I want you to see. Right there? Okay. So it turns out to be about 29%. Notice that we are not quite at the peak. There's a lot more, right? Like 20% is hiding in this little interval from the edge of my line to the peak. Does that make sense? So if I just graph here, x equals 1518. Yeah. So that little sliver there is actually 20% of the area of the whole, underneath the whole curve. It's kind of cute. Okay. Feeling better about the central limit theorem?
Yeah.
Okay, when does the central limit theorem apply? Normal distribution when we have a mean of a group. Mean of a group.
Mean of a sample of the population.
Okay, or to be more precisely, it's the mean of a sample of a population. Thank you, Michael.
Yeah.
You're, when I'm grading your test, I'll be thinking, man, he made such great comments in class, except when he wasn't screwing around with the blinds. So, no. So you can use this. So let's go back. Where'd you go? Right there. So you can use this formula for the standard deviation under essentially three circumstances. One is that you have any population and your sample size is greater than 30. And you're talking about the means of each group, not the individuals. That's important. It's got to be the means of the group, not the individuals. We have to compress the data for this to be relevant. And then if you're less than 30, then you either have to have a population you know to be pretty darn close to normal, or you know to be pretty darn uniform. What does it mean to be pretty darn normal or pretty darn uniform? That's a whole nother question we're not going to address. Yeah. I was thinking about getting a special wireless unit for this room. All right.
Sometimes if I disconnect
And reconnect, it gets better, yeah. Yeah, one problem we have is that more and more people walking on campus with smartphones that are automatically picking up the connection, which slows it down for everybody else as they, go to Facebook and YouTube and other stuff. All right, let's see. Does anybody have another question for me, or shall I pull out one of my questions? Okay, I got one for you. Ready, set, go. So, I mentioned that guy I found on the internet, and I'm sorry, Guy, I'm not citing your name right now. I will do that soon. I found a guy on the internet who's obsessed about M&Ms more so than me. And didn't I say this already in the beginning? Oh, you weren't there yet. Yeah, so this guy measured 800 and something M&Ms. He found their average diameter with a micrometer and masked each one of them. So these measurements are in millimeters for diameter and grams. And he also sorted them by color and type. So he has plain, peanut, and peanut butter M&Ms. He describes exactly how to figure out what he means by average diameter. He gives a whole paragraph description about exactly what he means. This guy is awesome. So if I remember what he wrote properly, if I were to draw a plain M&M, it looks, something like this. That's a shitty job, isn't it? Okay, let's do a cross section of a plain M&M. Looks something like that. If I slice it through its center, so that it was resting on the table with the M facing up. Right? And then I slice straight down perpendicular to the table it is sitting on. And I get it right through the center of the M&M with my slice. Then he's got the average length of that slice perpendicular to the cross section. See what I mean about a paragraph describing exactly what he means by diameter? If you're doing studies where you have data, you really got to be pretty precise about how you took your measurements. So yeah. So if you were an analyst for M&M and they wanted to know, hey, are our machines doing a good job making these? You need to do this stuff. So there are people like me that are paid to do this. They're paid to weigh and figure out what's the best procedure for doing all this stuff, and then tweaking the machines to make them do good, right? Because how many people like those M&M minis? You like them? I don't like them. They're too small. They just don't work for me, right? And before I've seen bigger M&Ms, and they were too big for my mouth. These are just right.
You don't like the M&M minis?
No, I hate them. Too much candy, not enough chocolate. I don't like the hard candy shell as much as I like the chocolate inside. Yes. Well, it depends small. Like too small is not good enough. Too big's too much, right? Okay, anyway.
I want to know the perfect air to chocolate.
Yeah, the candy coating to chocolate ratio.
No, he didn't talk about that, but that came up in the previous class. So the question was, what is denser, the candy coating or the chocolate? I was thinking the candy coating because it seems harder. That doesn't necessarily mean denser, because like ice is harder than regular water, but ice is less dense because of the way the molecules form these cute little rings with air pockets in them. But the chocolate is more moist, so maybe somehow that moisture makes it somehow denser. But chocolate is also whipped, so there's some air in there. So we weren't able to answer that question. That's for a future study, which is more dense, the candy shell or the chocolate inside. Okay, let's do a math problem. Okay. Okay, what is it, Michael? Yeah.
In high school,
Yeah.
my science teacher told me, or said to the class that if all the ice were to melt, or whatever, the water would raise, the ocean water would raise however much.
Yeah.
And I said that ice is less dense than water.
Yeah.
And that most of the ice in those ice caps are underwater.
Yeah.
So melting it wouldn't that lower the water's level? Because majority of it, if you see pictures of ice.
Yeah, no, it turns out if you do the calculation on the percent change in density of ice to water, it's still enough difference that the melting of the ice caps will raise the water level.
It's under the majority of the ice cap is underwater.
I know, but the percentage under the water is not greater than the percentage less dense ice is compared to water.
It would go down if you were to grab.
Well, we can.
Take it out completely.
Well, if you take a water.
Okay, we'll have this discussion later. Okay, we got to do some math now. That is great math, but it's not relevant to what we need to be doing for the test. Okay,
Wait,
yeah.
what's the test?
Friday.
What?
Oh shit, the test is Friday. Okay, back here. So, okay, so here's the first thing.
Friday?
When you take the test, Friday, yeah. So I was looking at M&Ms, and I was, for some reason, enamored with the blue color, because it's spring and the skies are bluer than usual these days, it seems, compared to the gray of our winter. So blue caught my eye, and I took 5 different samples. I labeled them A, B, C, D, and E, and that's kind of a small font. Let's blow that up. Okay, can you read that kind of now? All right, so let's pick on sample D. Sample D, I found 16 blue M&Ms out of a total of 54 M&Ms in the bag. The bag of M&Ms, by the way, weighed 48.23 grams, which gave each M&M an average mass of 0.89 grams. Okay. So, question. Is it unusual to find 16 out of 54 blue M&Ms in a bag? Can I answer that question without more information? Okay. Gary found 16 out of 54 blue M&Ms. Is that unusual? Okay, so you can only answer an unusual question if you're comparing it to something. And so at the moment I have nothing to compare to. However, checking with the manufacturer of M&Ms, they believe that blue M&Ms, plain, which is what I'm talking about, should be 10% of what they produce. 10% of the plain M&Ms they produce are blue.
Do they have like a margin of error, like plus minus?
They do, and I didn't record that, but I don't think I found it on their website, but I remember seeing it somewhere else on the internet. So Mars, the company that makes M&Ms, produces 10% blue. Now we can answer the question as to whether this is unusual. Okay, so this is about, so my bag had about 30% blue. Okay, so 30% is higher than 10. The next question is it a lot higher? If so, what is your measure for a lot? How do you measure a lot higher? So, That's not, sometimes 200% higher is not a lot. What do we do to figure this out? So what should I expect to get in a bag? I should expect, okay, so what's 10% of 54? That's what we call the expected value. An expected value is percent times count, which is 5.4. So I expect to get 5 or 6 blue M&Ms per bag that has 54 in them. I found 16. Okay, it's higher. So the next question is it unusually high? Is 16 out of 54 an unusually high number of blue M&Ms? How are we going to measure that? What kind of distribution am I talking about here? Nope, we got to measure stuff. That's the whole point of this class, measuring stuff. What's that? We could look at standard deviation. Standard. What kind of distribution is this, though? It's not normal. It's a discrete binomial distribution. Yeah, this is binomial. So the standard deviation of a binomial distribution is the square root of NPQ. So in this case, I would take 54 times 10% times 90%, take the square root of that. Yeah, so 54 times 10% times 90%. So 54 times 0.1 times 0.9. Anybody have a number there? 16.2? Really? That doesn't sound right. 2.2, that sounds better. Okay. So the distribution for finding some number of blue M&Ms in a bag of 54 has a mean of 5.4 and a standard deviation of 2.2. So we talked about what's called the range rule of thumb, which says that you should expect about 95% of the data to be within 2 standard deviations, mu minus 2 sigma, mu plus 2 sigma. And our standard deviation is about 2.2, so let's see, 5.4 minus 2.2 twice gives me what, 1? And 5.4 plus 2.2 twice gives me 9.8. Okay. Now where the hell did I get 95%? Empirical rule. Empirical rule applies to what kind of distribution? Normal. Is it always okay to apply normal rules to a binomial? Turns out no, it's not always okay. You can always get away with it if the probability of a success is 0.5 or pretty close to it. What's my probability of a success? No, it's 10%. Yeah, that's the probability of getting a blue. Is 10% close to 50%? No. Okay, so might the empirical rule be kind of useless here? Yeah, it might be useless. Well, I can double check that, but so is the range rule of thumb always relevant to binomials? The answer is no, but sometimes we use it anyway. What this says is 95% of the time I expect to have between 1 and maybe 9 blue M&Ms. What did I find? 16. Does that seem outside of what's expected? Yeah, okay. So, but that calculation isn't foolproof. The next thing I do is I look at a tail. So I'm just going to make, ooh, crazy pen. I'm looking at a bag of 54, so it's possible I could get no blue M&Ms. It is also possible I could get 54 blue M&Ms. It's not likely, but it's possible. What is the expected value of blue M&Ms that I'll end up with in a bag of 54? which is 5.4, so that lives somewhere over here. Okay, so that's going to be the highest stack in my distribution, and then it drops from there and drops sharply from there, and then it gets wicked small in the tail. That's what this distribution is going to look like. It is skewed to the right. Excellent. 16 lives right about here. So to figure out if 16 is unusually large, I need to calculate the probability that x is greater than or equal to 16. Always do tail probabilities. And if that probability is less than 5%, then we say 16 is too big. Okay, it's got to be a tail. This is a binomial distribution, so I'm going to use the binomial CDF. But what's the problem with the binomial CDF? It only does left tail, so to calculate that, I'm going to have to do 1 minus the left tail, because I want the right tail. So I'm going to have to do 1 minus the binomial CDF. N is 54. P is 0.1. And let's see, I want to keep 16. I want to get rid of anything below it. So what's the first number below it? Yeah, so then I would get rid of from 15 and below. So that's the calculation I need to do to figure this out. And the Excel is pretty darn similar formula to this one, except the order of the numbers is different. Yeah. All right, so I want 1 minus the binomial CDF, option B on my calculator, 54 trials. I'm pulling out one M&N at a time and I'm looking at them. Is it blue or not? Is it blue or not? Probability that it is 0.1. I'm concerned about 15 or less and 16 or more. And I get 0.00005-ish. I get that this tail right here has a probability of about 0.00005. Now, usually the homework allows you to round to 4 decimal places. My mother would like you to round to 3 decimal places. So to 3 decimal places, what is the probability I should find 16 or more blue M&Ms out of 54? 0. Yeah, so this is an unusual event. This is unusual. So according to this calculation, it is very unusual to find 16 or more blue M&Ms out of 54.
Whoa.
You all right over there, Michael?
Yeah, it said fantastic, and then it gave me a paragraph.
About why you were fantastic? It is very unusual to find 15 or more blue M&Ms out of 54. All right, so how are we doing? You getting ready for a test? Not looking forward to it. So there's 2 sample tests, and there's some solutions to each of those questions on the sample test, but not all. Get your homework done, read the book, get some sleep, try those sample tests.
Is the test going to be kind of similar format and order of the samples like test 1?
It's going to be pretty darn close to this one right here and the other. They're both pretty similar, but shorter. This test is way too long here.
Is it like,
Wait, how many problems are
this one's only 9 questions. Really?
It's going to be more like the length is going to be more like the first one. Yeah. Some of them have multiple parts.
That one had like 13 or 14.
Plus 4 subparts for each part. Yeah, this is the second test I posted has like twice as many questions as I can possibly give you in 50 minutes to solve.
I was looking at some.
And then, here's what I'd like you guys to try to find time to do today. Email me an interesting binomial problem. Email me an interesting binomial problem. Make one up. You had to do it anyway for your lab. Yeah, the last lab.
That's right.
Haven't gotten to that. What's that? I'm not doing a take home on this test. Do you want one? How about the
How about you don't say what you're about to say?
why?